Have you ever looked at something totally random and wondered if there's a secret pattern hiding inside? You know, a rule that can take complete chaos and somehow, almost magically, turn it into something predictable? Well, today we're going to dive into one of the most powerful ideas in all of statistics, a concept that finds perfect order hiding in plain sight.
The whole idea really boils down to this one simple question. We all get that rolling a single die is random, right? A 1, a 6, any face is equally likely to pop up. But what happens when you roll 2 dice and add their values together? Or 5? Or what if you roll, say, 1,000 dice? Does it all just stay a jumbled mess, or does some kind of hidden pattern start to show itself?
And this right here is the mystery in a nutshell. On the left, you've got the outcome of a single random event, a die roll. It's a flat line, what we call a uniform distribution, because every outcome is just as likely as any other. So how in the world does that flat, unpredictable line transform into this elegant, perfect bell curve on the right, just by adding lots of those random events together? Where does that shape come from?
To figure that out, we're not just going to talk about it. We're actually going to watch this pattern emerge right before our eyes. This isn't just some abstract theory, it's something real and observable.
So let's do a little experiment. We're going to simulate rolling a whole bunch of dice and adding up the results thousands and thousands of times. Just watch what happens to the shape of the data as we increase the number of dice for rolling.
Okay, let's start small with a sum of just 5 dice. And right away, you can see something's happening. It's not flat anymore. See that? The results in the middle are already popping up more often than the ones at the ends. And that kind of makes sense, right? There are a lot more ways to roll a total of, say, 18 than there are to roll a total of 5. So a little peak is starting to form.
All right, let's double it. Now we're looking at the sum of 10 dice. And whoa, look at that. That central peak is way more obvious now, and the sides are starting to slope down. The randomness is actually starting to get organized. Now we're jumping up to 50 dice, and there's just no mistaking it. That classic bell shape is really taking form. It's getting smoother, more symmetrical. And finally, the sum of 1,000 dice. Just look at that. It's a near-perfect bell curve, what statisticians call a normal distribution. It's incredible. We started with the flat, chaotic roll of a single die, and by just adding enough of them together, we ended up with this beautiful, predictable shape. The chaos has literally resolved into order. Seeing it happen is one thing, but that just leads to the bigger question, why? I mean, what is going on here? It really feels like magic, but it's not. It's pure mathematics. There has to be some kind of rule forcing this to happen. So, to understand the why, we gotta peek under the hood a little bit. There are 2 really simple rules that tell us what happens when you combine random numbers. These rules are going to help us figure out where our curve is and how wide it is. Okay, rule number 1 is about the average or the mean. And it's super intuitive. The average sum of 2 dice is just the average of the first die plus the average of the second. Simple. The second rule is about variance, which is just a fancy word for how spread out the results are. And for independent events like dice rolls, the spread also adds up. So the more dice you roll, the wider the range of possible sums becomes. Makes sense? Now, this is the crucial part. Those 2 rules are great. They tell us exactly where the center of our bell curve will be, and they tell us how wide or skinny it will be. But they tell us absolutely nothing about why it's a bell curve to begin with. They don't explain the shape itself. For that, we need the main event. And here it is, the one concept that explains everything we've just seen. It's called the central limit theorem, and honestly, it's one of the absolute cornerstones of probability and statistics. This is the secret sauce. So what does it actually say? Well, in plain English, if you take a whole bunch of independent, random numbers and add them up, their sum is going to start looking like a bell curve. And here's the truly mind-blowing part. It doesn't matter what the original randomness looked like. We started with a flat line from our dice, but you could start with a U-shaped distribution or something totally bizarre and spiky. Add enough of them together, and you still get that same perfect bell curve.
This is the big takeaway. Let's just put it as simply as possible. The bell curve is like this universal destination for the sum of many random things. It's a fundamental pattern that's literally woven into the fabric of probability.
Okay, so this is a fascinating idea for sure. But is it just a cool party trick for statisticians? No way. It turns out this is one of the most powerful and practical tools for solving all sorts of real-world problems.
So, where does its power come from? It's a shortcut, a massive one. It lets us swap out really messy, complicated probability calculations for the much simpler, well-understood math of the bell curve. This saves a ton of work and lets us get incredibly reliable answers to questions that would otherwise be a nightmare to solve.
Let's take coin flips, for instance. Figuring out the exact odds of getting, say, exactly 63 heads out of 100 flips is a horrible calculation. But hang on, the total number of heads is really just the sum of 100 little random events, right? That's a perfect setup for the central limit theorem. So instead of doing the brutal math, we can just use the bell curve as a stand-in, a super accurate approximation. All we have to do is find its center and its spread, and we're basically done.
And look how well this actually works. For getting 20 heads in 40 flips, the exact difficult answer is 0.1254. And the super easy approximation using our theorem? 0.1256? I mean, come on, they're practically identical. That's the power of this tool right there.
And it gets even bigger. The theorem doesn't just work for sums, it also works for averages. If you go out and take a bunch of random samples from a population and calculate the average for each one, guess what? The distribution of all those averages will also form a perfect bell curve. This right here, this is the bedrock idea that makes things like election polling and scientific research even possible.
So let's zoom out one last time and just appreciate how huge this is. This isn't just some abstract thing in a math textbook. This is a fundamental principle that actually describes how huge parts of our world work. Once you know what to look for, you see its fingerprint everywhere. It's the reason a poll of just 1,000 people can accurately predict an entire election, because the average opinion follows this bell curve. It's used in factories for quality control, because they know that tiny random variations in a product will add up to a predictable pattern. It even helps explain why natural traits like human height form that familiar bell curve shape across a population. It is everywhere. So, when you get right down to it, the central limit theorem is about finding certainty where you'd only expect to find uncertainty. It's the rule that shows us how a whole bunch of random, chaotic, unpredictable things can somehow work together to create a predictable, orderly, and, yeah, even beautiful pattern. And that's the thought I want to leave you with. Now that you know about it, where else are you going to see this pattern? How many of the complex systems in our world, from the stock market to our own biology, are really just the sum of many small random parts, all secretly marching toward that same predictable bell curve?